All right, so let's start with a new topic. This is called containers. Technically, you know about containers already. There's a little bit more to say, though. C++ has a lot of stuff that holds stuff. That's the metaphor. We're holding on to a bunch of stuff. Okay, so let's store some stuff. You know vectors already. Vectors are a way to put a bunch of things in one place. You know arrays. That's another way to put a bunch of things in one place. Linked lists, competitor to vectors and arrays, right? You've read about that at least. We briefly touched on it. C++ gives us a bunch of classes to store stuff. Let's talk about some others. But in general, what are they all? Like a vector is something called an ADT, an abstract data type. So let's talk about that first. All right, so an ADT, which every container I'm about to teach you today, it is this thing called an ADT, so that's why we're going there first. So an ADT is, if you go to like a textbook, it says a class of objects whose logical behavior is defined by a set of values and a set of operations. So when you hear ADT, think vector. All right. So it's like a black box. It's a C++ class that's a black box that you don't really understand how it's implemented, but you know that you can do stuff to it. All right. It's defined in terms of its operations. That's the idea. Your little black box, this thing that you're interacting with, you can talk to it and give it method calls, and it can give you things back, but you don't really know how it's implemented, and you also don't care. That's the beauty of it. So like vectors are an abstract data type, because how have you interacted with a vector? Just by telling it to do stuff. You have no clue what's going on inside this vector, do you? I have not told you. You don't have to care. All you need to care about is like, does it respond to the things I ask it to do in orders? Like if you say push back on this vector, push back 2 or something, and then it responds, you say that, push back 2 please, vector, and then it responds like, well, it's a void method. It's like, sure, I'll put that in there for you. And then all it means to be a vector is that it responds to, like, if that was the first thing you put in, it responds to you asking .at of index 0, and it will give you back 2. Right? That's what it will respond with. That's the first thing you push back. Any black box that plays this game is a vector as far as you are concerned. Does that make sense? It's defined in terms of its operations. That's what it means to be a vector. As long as you give access to these kinds of operations, push back, pop back, at, size, you have a vector at your disposal. So you don't even care if deep down, like, is it an array inside of that? Is it a linked list inside of that? You have no concern for that kind of information. That's what it means to be an abstract data type. It's defined in terms of its operations, all right? So a container, then, is a type that holds a bunch of stuff. So you can have an ADT that is also a container. So a vector is a container, and you can put whatever you want inside of a vector, including other vectors, right? Have you tried that? So a container is usually also an ADT, and we're going to talk about a bunch of different container classes today that I won't really tell you how they're implemented. I'll just tell you what you can do to them, because that's all you need to know. Okay, so let's talk about vectors first, and then I'll talk about iterators, which I don't think we've touched on in this class yet. So what else is there to know about vectors? So a vector is a container. It's what's called a random access container, by the way. Let's go to the documentation for them. Containers, what do you know? You know that word now. Vector. So vectors, you know what they are. They're things that hold things. Sequence containers representing arrays that can change in size. So you can read this now and probably understand it for the most part. So a vector is a random access container. What does that mean? What does that term mean? That means that you can go anywhere immediately in it. So like if you have this vector 8, 6, 7, 5, 3, let's say, and this is your vector v, then you can go to each individual place with an index. That's what it means to be a random access container. I can go to the middle of it immediately, just go to index 3. It'll go there, do the .at. So I can go to index 2, do the .at. You can go somewhere in the middle. That means you have an index, so you can immediately get somewhere. Linked lists, remember, did not have that ability, right? You couldn't go through the middle. And to get to an index, this random access place, use the dot at, and that is a very fast thing. It's a constant complexity operation. So constant is the best possible complexity, by the way. It's as small as it could be. And most vector operations are in fact constant time. Dot at is constant. Dot size is constant. Dot pushback is constant, surprisingly. So if you want to add something to a vector, you say dot pushback, and it's constant time to do that. Add something to one index after the end there. And so that's kind of cool. That's as good as it can be for those kinds of things. If we want to just do these things, you can't get any better than a vector. Okay? The name of the game today is that sometimes we want to do more than just this, or different things. So that's vectors. And like you can move around a vector with dot at and dot size. You can set up a for loop with indices, right? There's another way though. So let's talk about that other way. It's called using iterators. Right? You can use an iterator instead, and those exist here. Iterators section. You got begin and end, and then some other things that we don't want to get into. So if you say v.begin, that gives you back an iterator into the beginning of the vector. You say .end, that gives you an iterator to the end of the vector, and you can use those to go through things. So here's the silly looking syntax. I'm going to explain it in just a second. But all of these container classes, even though they're going to look weird soon, they're all going to have these iterator things implemented for them. So let's talk about that. An iterator is just like another type. It's a class that abstracts over what it means to iterate through something. So they're modeled after pointers, so like pointer style things work for them. But here's the idea. Here's the setup. If you have a vector v, you can go places in it using iterators. All right. So if you ask for v.begin, that gives you an iterator to the beginning of the vector v, and you think of it like a pointer. All right. So if you make like an iterator variable and you say it, call it it equals v.begin, that gives you back an iterator. It gets set to be an iterator to the first element of this vector. Oops, so it's kind of like a pointer. That's what I want you to think of it as. Okay. So that's the idea. It's a bit of a disgusting type. If you make a vector of ints, an iterator to the start of it, v.begin, gives you back this type. The iterator type lives within the vector type. It's kind of weird. You say vector int : iterator. That's the type of the thing that begin gives you back. All right, so that's begin. And then end, v.end, is also an iterator. It gives you an iterator not to the very last thing, but to one past the end, I'll say. So this is where v.end will take you. And so you never want to go there, right? That's one past the end. You want to stop before you get there. If your iterator it ever gets to here, you are done, okay? So v.end is an iterator to one past the end of your vector, and so you never want to get there. You don't want to dereference it. And so iterators, they're modeled using pointers. You can say, if you say star it right now, for example, the star operator is overloaded. That will give you back 8. And you can also say it++. That will advance the iterator, and so now it's looking at the 6. If you say star it now, it'll give you back 6. Okay, so that's what's going on. Think of it as pointers, and we'll go from there. So let me give you an example of all of this now. Now you know all we need. So this is another way to iterate through a vector. So a vector is a container. It can hold a bunch of stuff. And one way to go through a container is to iterate through it using an iterator. So let's make a vector. And there you go. And I would like to make an iterator to the beginning of v. I can say it equals v.begin, but I gotta give it its type. What is the type of this iterator? It's vector int : iterator. So an iterator through a vector of ints is different than an iterator through a vector of doubles. It's a type within a type, kind of. And so all of the pointer style stuff works. Like you can say star it, and that will print the 8. it++ will get it ready to go to the 6. And now star it will print the 6. Boop. So I see 8 and 6 printed out. Questions about that? Does that make enough sense to us? It's a new little concept. But I can use these iterators to go through the vector like this. here's a standard for loop that uses iterators. For vector int colon colon iterator it equals v.begin. And I want to keep the iterator going as long as it's not the end. We want to stop before we get to the end, so go until it's equal to the end. Well, it's not equal to, continue. And then it to advance it each time. So that's how you do that. And you can be like, cout star it, you got a new value at it every time. And relay. That is another way, another valid way to go through a vector. And that's going to print the whole thing. Any questions about why this code is going to print the whole thing? Iterators, they're like modeled on pointers, and it's just a wrapper around moving through this container, this vector. Oops. So, this is ugly, right? This code looks really ugly. You don't usually use it this way. Remember that range-based for loop? For int x and v, that's so clean and beautiful. Remember that kind of code going through a vector? This code secretly uses iterators. This gets translated. This exact code gets translated into this exact code. Believe it or not. So that's kind of cool. That's what's going on secretly. And deep down, one way to implement really iterators on vectors is to use pointers. So they really are pointers, kind of. So here's the idea. Here's how I want you to think about the iterator. So here is our vector, 8, 6, 7, 5, and then instead of indices, let's use addresses. Like this is address 100. If they're ints, the next one will be 104, 108, 112. And then the end, one past the end, would be 116. We never want to get there. Right? So what we were doing in our code was we were setting up it to be initially v.begin. So it was holding the address of the first thing. Boop. And when we said star it, we printed it and we got the 8. And then we said it++, which advanced our little pointer. And then we said star it space it++. And it's still not equal to the end. Star it, it++, 7. Star it, it++, get the 5. it++ one more time. Now this is one past the end, and that's exactly what address, essentially, v.n will give back. So now it is equal. We want to stop early. That's what's going on there. That's how that's working. I hope that makes enough sense. So that's vectors. There is a list type in C++, and so let's talk about that. And this will also answer the question, like, why in the world would I ever want to use iterators? They look so dumb. It's because the C++ standard library implementers have been very nice to you. They've made one kind of idea, iterators, that lets you go through anything, any kind of container. It's like a list. Remember reading about this in your book? Like, you make a linked list, 8, 6, 7, 5. Remember how disgusting it was to go through this whole thing? To iterate through it? Well, C++ is giving you a very easy way with their list type. So let's go there. List is very similar to vector. It's modeled essentially in terms of a linked list, so you can't really go to a specific spot. You can start at the beginning and the end, though. So great for iteration. And you can add things to the front and the back. Push front, pop front, and push back, pop back. That's lists. So yeah, list, I want you to think about it, like really deep down, it really is implemented using a linked list. But you don't have to care, right? You just need to know what it can do for you. That's what it means to be an ADT. List is an ADT that responds to push back, push front, pop front, getting the size. And lists are better than vectors at some things, like insertion and deletion to the back or the front are constant time. You weren't even able to add to the front before in a vector very easily. There was no method for that. So now lists can do that just fine, and it is constant complexity, which is beautiful. So yeah, let me show you some list stuff. Let's make a list. It looks exactly like it's the list header. Works very similar to vectors. It's a temp, like you say what kind you want. So let's go here, lists.cpp. Boop. So I'll include the list library, and I'll make a list of ints. Call it L, and then I'll be like L.pushback 3. So this is just like vectors. Pushback 4, but I can also push front. L dot push front. I don't know. Let's make this in order. So push front 2, and then we'll push front a 1. Oops. I keep pressing the wrong key. So after all these, it will be the list 1, 2, 3, 4. Does that make sense in your head? So 3, 4, 2, 3, 4, 1, 2, 3, 4. All right. So that's lists. Add to the front and the back, which is quite nice. You also get iterators through lists. Even though there's no .at, the iterators work exactly the same. You still get begin and end, and you can still use them in the exact same way. They're completely different kinds of types, but the iterators work the same. It's just a list int iterator it this time. And so the vector int iterator it. And I guess the whole world is looking at the iterators documentation. It's not loading for me. That is very unfortunate. Step. Try again. Oh well. In the meantime, you get the idea. I'll draw it. So here's the list that we just made. Essentially, it's like a linked list. 1, 2, 3, 4. And if I'm going to make an iterator, I say it equals L.begin, and it'll just go there, and I can get the 1 that way. It's perfect. The iterators work the exact same way, and you can use the range-based for loop again. That also works still. It's beautiful. Everything works as you would expect. So there's the begin again. Here's the example. It looks exactly the same as the vector example, which is really, really cool. So yeah, let's make that happen. Same exact code to go through this vector, this list. For list int : iterator it equals L.begin. It is not equal to L.end. Keep going until this is always 1 past the end, right? And then advance it, it++. See out star it, and then a space. So that's that. And that will give me my 1, 2, 3, 4. In the exact same way as it did for vectors, but it's a completely different type. There's no guarantee this would have worked, but the C++ library people did it for us. So that is that same looking code does the same thing. And so again, what's going on is it's kind of like a pointer. It starts here, you say it++, like start it right now, would give back 1, and then you advance it with it++, which would bring it to the 2. Now star it would give you the 2, and it prints the 2. it++ gives you the 3. it++ gives you the 4. And then it++ one more time, like, gives you nothing, right? Because the thing after the 4 is emptiness, so it gives you, like, null or something. It's like a null pointer. And so that is maybe what L.end gives back. It's like, make sure it's never equal to null, because that's when you know you're done. So that works. You can also do it-, by the way. You can move backwards. That's okay. There's also reverse iterators if you want to do that in a cleaner way. It's like reverse iterator begin, reverse iterator end. That's over here. So that might be something you want to look into. R begin and R end, if you want to do it that way. But either way, it's fine. It's happy. And yeah, the range-based for loop works exactly the same on lists because it gets translated into this code. So let's show that too. Did I do that on vectors? Let's do it on lists though. So for int I in L, this exact code is being translated into the code above. So it's just going to print it out twice, but the second way is the cleaner way. But it's secretly using iterators. It's being translated. This code is being translated into this code, which is really cool. So that is the list container. Any questions about that one? All right, I got some more for you. Let's do set. Set is a type. A set stores unique, a set of t's, whatever your type you choose, it stores unique t's, like unique ints, unique doubles, unique strings, in order. Ooh, it's kind of cool. So here's the set type. It's another container. Works completely different to lists and vectors, but again, it has iterators. That's the goal. You can insert stuff into a set. You can see if it's there. The idea is seeing if it was there or not. So let's see here. It stores things in order. So if I insert, let's say I make a set S, it's like a cloud. Think of it like a cloud. It orders itself. Do you have it or do you not? Let's say I insert into the set S 2, 2, 1, 3, 0 in that order. So it's like, okay, I insert the 2. It's like, cool, I'll put the 2 there. And then I insert the 2 again. It's like, I don't care. The 2 is already in there. It only keeps unique ones. So it's not going to hold duplicates. And then you insert the 1. It's like, okay, I'm going to keep things in order, so I'll put the 1 here in a special way. Then you insert the 3, and it's like, okay, I'll put the 3 here. I'm going to keep it in order for you. It's really nice. And then you insert the 0. It's like, all right, 0's not in here. I'll add it, and here's the order. So this is going to keep things in order. It's going to keep them uniquely. It doesn't care about duplicates. Just like, was it there or was it not there? So it's like a set of things. And it responds to commands that look like this. Insert, put something in. Count tells you if it was there or not. It's like, count how many 2's are in the set right now. And the answer is always going to be 0 or 1. There's a reason it's called count, though. It's trying to keep it similar to other types in the library. But count's really only going to return 0 or 1 if it's there or not. It's just, was it there or not? And then erase gets rid of something from a set. And all of these operations, they're not constant, but you're also getting ordering out of this, so you can't really expect it to be constant. But it's logarithmic complexity. So to add the next thing, it's going to take, like you have 4 things in here right now, it'll take about log base 2 of 4-ish basic operations to add the next thing in if the size currently is 4. That's the idea. So that's really fast considering you get ordering out of this. And that's what sets are doing. They know the order of their elements, and that's why when we iterate through them, we're going to get everything out in sorted order, even if we put things in a weird order. You can use begin and end exactly as we would expect. It's going to iterate through this cloud, and I have not told you how this gets implemented at all. But you don't have to care. It's an ADT. So I'll include the set header. I'll make a set of ints called S, and I'll insert exactly those things in that order, 2, 2, 1, 3, 0. S.insert 2, again, 1, 3, 0. And so now you can ask it things like, hey, are there any 2's in here? And it will say yes or no. Count how many. Are there any 1's in here? Are there any 42's in this set? So it's really just going to return 1 for yes, it's there, and 0 for no, it's not there. Because there are no duplicates. It's not going to say 2 2's. It'll be like, all right, yes, there's 1 2 in there. There's 1 1. There are 0 42's. That's how you know if it's in there or not. That's what sets are good for. But you can also iterate through them. So for set int : iterator it equals s.begin. It is keep going as long as it's not s.end, because that's 1 past the end of the set. It++ to advance it. Cout star it. And a space. This will iterate through the set in whatever weird way it needs to. The library people have taken care of that for us. And we get everything, even though we didn't insert it in order, we get it back in sorted order. Isn't that lovely? So that's pretty cool. And that is sets. It's just another type. It does some things cooler than other things. Right? It's good at keeping things in order, even if you put things in out of order. You don't get that for vectors and lists. Right? This is a new idea. It's very cool. So there's that. And then, let's see here. Dun, dun, dun. Let's do one more. Map. So a map is pretty much a set, except it holds pairs of things rather than a single thing. There's 2 things involved when you have a map type. It's called the key type and the value type. So you're storing keys mapping to values, all right? So a map maps keys to values. And so a good example of a map is like a phone book. I don't know if, do we all know what a phone book is? They don't get them out anymore these days. But it used to be a giant book, right, that held, like, you go and it's in alphabetical order, and it tells you a person's name, and it tells you their phone number. You go and look up their name, and it tells you their phone number. So it's a lookup table, essentially. So it's going to be a map from string keys, that's the name of the person, to int phone numbers. Does that make sense? That's the goal. So that's why this map type takes two types, a key type and a value type. You're going to use the key type to look up the value, the associated value. So here's the map type. It takes two things, two types, a key type and a value type. And you can put stuff in with the emplace method. I'll show you that. You can make a map from characters to ints. You give two things in those angle brackets this time. So this is a map from string keys to int values, and that's a phone book. So if I make that and I call it phone book, or M for short, it's another cloud. It's going to store the keys in order, but it's going to store pairs. So it's like I'll insert my name mapping to my phone number, 5551234, I guess. And you could insert somebody else's phone number, like their name. I'll give my cat a phone number, 5551235. So there's that. And so this is the key. It's the first thing. And then the value is the thing you're storing associated with that key. This will make sense when I give it to you as an example. So yeah, the idea is, given a key, you can look up the value associated with it. There's a .at method on maps. It's like go to a certain key. It takes the key and it gives you the value that's stored at that key. It goes and looks up their name and gives you back their phone number. So that's the lookup process. And maps are just as fast as sets. Everything is logarithmic time to insert, retrieve, etc., etc. So let me show you an example of that. So it all works the same, though. It's all got iterators. I hope you see the patterns. That's what I'm getting at here. Let's make I guess I need the string type, too, if I want to make a phone book. So if I make a map from string names to int phone numbers, call it phone book. Right now it's empty. I can put stuff in it, though, with the .emplace method. So I can say phone book .emplace my name to my phone number. And you can do it for as many key value pairs as you'd like. Oops. There. And then you can ask, like, did I put something in there? Oh, sorry. It's the map header, not the maps header. Excuse me. And then you can ask it for, did I put something in there with a certain key? It's all through the key. Okay. My Vim is currently frozen. There it goes. All right. So I can say cout phone book dot count. Count how many thing is Lawton associated with some value in this map. Is my mom somewhere in this phone book? No. So you can check if it's inserted in there or not, just like that. And so, yes, there is something associated with the key Lawton. No, there is nothing associated with the key Lawton's mom. Okay, so there's that. And if there is something in there, at a certain key, you can get the value back. You can look it up with the key. Cout phone book .at, and then the key name. And that would give you, oh gosh, I don't actually know if it compiled and got the changes. Sorry, let's do it again. That would give you the value associated with it. So you look up the key and you get back the value. That's what maps are good for. Look up the key, get back the value. You can't go to something that doesn't exist. That would throw an exception. Just like for vectors, it's like invalid access. It's out of range, essentially, which is kind of cool to think about. So you can't do that, which makes a lot of sense. But you can still iterate through this entire thing. Of course you can, with begin and end. That is thanks to the library makers. But this kind of iterator for a map iterator it gives you back something. You can't just say star IT and get one thing because it's storing two, right? It's storing the key and the value, and so it's storing it as a pair of things. You can say IT arrow first and IT arrow second to get the first thing, the key, and then the value. But everything's going to be ordered and given back to you in sorted key order if you do it this way. So for map string int : iterator IT equals phone book dot begin. IT is not equal to phone book dot end. IT plus plus to advance it. Let me zoom out so we can see all this at once. There. What do I want to do with this? Let's just output every key value pair. See out IT, and you can't just do star IT. That gives you the pair, but you can go and get the first thing, which was the key, and then the second thing. It's easier to use the arrow though. So IT arrow first. That maps to IT arrow second. Let's use the arrow instead. Endl. So that'll go through the entire phone book. Print out our stuff. So in sorted order by string, so in alphabetical order. So those are the two keys and their associated values. So that's maps. If you have two things, you want to take something and have it map to another thing. Use it to look up some other thing. Any questions about that one? So, with that, I have one last set of questions for you. So get into groups and debate with each other, and then we'll come back and we'll do them all lightning fast. So answer all four of these questions as a group, please, and then we'll come back and we'll see which ones you're thinking. But I'll start the by clicker for the first one at least. So we'll do the first one first. So get ready with that answer, but I'll give you time to think about all of them. So go to the by clicker page, please. But which container out of these options do you think would be the best to hold Pokemon cards and their selling prices, because they're getting high up there these days when millennials start making lots of money? And, all right, what container would you use to store a group of people who are waiting in a line for something? What container would you use to store students on a roster? Like maybe you're going to take attendance or something. And then which container would you use to hold the last 100 days of Bitcoin prices? All right. So pick whichever you think is best. Try to convince the people sitting next to you that your idea is the best idea. But there is not necessarily one right answer for each of these questions. So pick whichever one you think is right, and we'll maybe have a little debate. So talk about all of these. I'll give you a few minutes, and then enter in the first one. Enter in your option for question one, and then we'll do the other ones after that. Okay? But you've got options. Remember what you can do to each of these vectors. Lists, you can push and pop the front as well as the back. Sets give you things in order, if you want ordering, but it gets rid of duplicates. And then maps are key value pairs, key value associations. Taking a name to a phone number, for example. So take another minute to think about the answer to all of them, but enter in your answer for number one first, please. That's already up and ready. All right. So what would we use to hold Pokemon cards and their selling prices? There could be multiple correct answers though, so get it in if you're willing to play. Maybe we're all asleep today. It's too close to finals. I understand. Thank you, those of you who responded, all 8 of you. So D, we're thinking D, and I think I would agree. I think you would want to map, right, the names of the Pokemon maybe to the double price. So map from string to doubles. But you could also just make a vector of pairs or a vector of something. You need both though, the name and their price. If you want to look it up, a map's a good idea. But if you just want to like print it all out, maybe a vector or a list or a set, I could see that working as long as you store a pair of things inside of each element. Okay. All right, try number 2. What do we think for number 2? I'll give you a few seconds to get in what you were thinking for that one. Group of people waiting in line, A, B, C, or D. What'd you decide? So it's all about what would you want to do with these people, right? You're making a program that keeps track of these people for some reason. Maybe they're eventually going to leave the line. That might be something you need to worry about. So yeah, let's see what we're thinking. Ooh, look at that. That's a pretty graph. We're thinking maybe A or B, and I can see that. So you just want to keep track of them. Like a new person gets out of the line, you push them back. I can see why that would work in a vector, yeah? Same with list. I think I would pick B though, because people waiting in line will eventually like get served or something, and then they need to go away from the front of the line. You can't do that on a vector, can you? Or you could do it, but it's very difficult. You have to like start shuffling things. So I would like list because you can add a new person to the end of the line by popping or pushing back to the list, and you can also remove somebody who just got like it was their turn at the front of the line by popping the front. See that? That's kind of cool. But yeah, I think those 2 would be the best options. All right, what about 3? Students on the class roster. Maybe you're going to use it to call attendance or something. Always you want to think about it in terms of how you're going to use this information. You got the data, what are you going to do with it? A, B, C, or D? And that informs the decision of how you store it. So yeah, what were we thinking? Students on the class roster. A couple more seconds to get what you were thinking in there. All right, we're thinking, okay, C. I like it. Interesting. It's just like you'll never have duplicate students, so I like that. That would work. And then yeah, maybe you're adding them in some weird order, but you like want to read them off for attendance in alphabetical order, so you can iterate through it. You're guaranteed to get it in order with the set. I like that a lot. But honestly, I could see any of these, like vector lists as well. Like you just pre-sort it, just put the students' names in some order. That's the order you care about. So yeah, I think that one's pretty vague enough to have any option. But I do like that we chose set. Maybe we were thinking about ordering by last name or something. So nice ideas. All right, last one. Last 100 days of Bitcoin prices. How would we store it? What would we do? Again, it all depends on your use case. Like, do you just want to like graph this? Do you want to like be able to immediately go to like last Tuesday's price? Tell me that immediately, please. That depends. So get in your option for number 4. What are you thinking? And then we'll talk about it. Again, there's no one right answer. It depends on how you're going to use this data. All right, so we're not so sure. We're barely thinking maybe map, but vector, set. No list, though. I'm not thinking list. I guess that makes sense. You'd want something to, like, I can see vector because, like, you can just go to, like, all of the indices very quickly. Go to each day. That's totally fine. Like, day 0, day 1, day 2, just use indices to move around, or maybe you're just going to like average them and graph them. A vector or a list would be fine for that. A set would work if you don't really care about like the day, right? You're inserting a bunch of doubles, right? Those are the prices. It would be a set of doubles. If you don't really care about like which was what day, it's just you just cared about how many times was it this price? How many times was it this price ever? Was it this price ever? Get them out in order, so that could work for that. I also like the idea of map, because you could map from date to price. That's another thing that you could do. If you wanted to look up an individual day, you could have a date type that like stores November 16th. You could look that up, and that would tell you the price for that day. You can look up October 31st. It will tell you the price for that day. So a map I could see as well. So I might pick map or maybe vector. Those would be the ones that I might choose for that one. But again, it depends on what you have in your mind. What you're going to do with it. Any questions about that? There is no right answer, but does the thought make sense? All right, if we are happy with that, that's all of containers I want to talk about. I have another set of slides though to go through. So, boop, boop. I'm excited for this one. I'm going to teach you not C++. So I'm not going to test you on that. This would be evil, but I want to teach you some new languages, because depending on where you transfer to, assuming that's your goal, it usually is for a computer science major. Depending on where you transfer to, some schools like to teach C++ first. Fresno State does, so that's why we're doing C++ in this class. Some schools like to teach Python first, like UCSB, where I went to grad school. They do Python for their intro class. Other schools are stuck in the 90s and they teach Java first. So I'm going to teach you both of those languages, Java and Python. So you know a little bit, and honestly, it's going to not be too bad, because once you learn one language, you can learn the rest pretty easily, if you haven't tried that yet. I guarantee it's not the worst thing in the world. So I will prove that to you a little bit today, and then we'll do some more next time as well. But I want to start with Java, okay? I want to teach you Java because it's very, very similar to C++. C++ existed before Java, and so Java was like, we'll take some things from that we like, and a lot of things were taken, okay? So surprisingly similar to C++, it is an object-oriented language, so there's classes all over the place. Java hits classes even harder than C++ does, but honestly, it's not too different. There's a fun website called learnxandyminutes.com that I encourage you to look at, like to learn stuff. They have a Java page. It's just a long little page that like goes through Java stuff. I think I gave you this link for C++ at the start of the semester. Maybe you read that. But just like you start scrolling, it's going to teach you Java slowly but surely. Like here are the types. They look similar. Scroll. Here's how you print stuff. Here's how you do if statements and for loops. They're all there still. Here's how you make classes and make methods and things. So feel free to read that. It's a quick little intro to Java, but I'll give you some stuff too today. So, all right, let's do Hello World, of course. And so I'm going to make a file called helloworld.java, because that's the extension. It's not .cpp for Java programs. It's .java for Java programs. All right, and we're going to use the Java compiler, and it's going to be great. And I'll try my best to explain it as we go, because it's a little bit different. All right, so Java is very, very specific. It's very picky about what it wants for file name. So if I say hello world.java, it's usually capitalized like this. They like their capitalizations in camel case. I'll make a file called hello world.java. If I make a file called this, Java is very object-oriented. If I want a main function, I have to put it inside of a class. So I have to make a class with the exact same name as this file. That's what Java is very... it really likes that. Very pedantic about that. So I have to make one public class inside of this file, and it better be called Hello World. I will get a compiler error if I don't do that. So if you say public class Hello World, and then you give some curly braces, and that's inside of the class you put a main function, even though it's like a method, right? Since it's part of the class now. Everything inside of Java is inside of some class, right? So in Java, everything is a class. If you just want a function, then you make it a static method. There's a word for that. Did you read about that in your book? I think it teaches you that somewhere, probably in the classes chapter. If you just want a function, you need to put it inside of a class somewhere. But you can make it not part of any object. You make it part of the class itself, and then it works more like a function. It's called a static method. And you need to put it inside a class. So hello world is a public class. You give the modifier next to it always. It is public. So it's visible to the outside world. Other files could look and find this class somewhere. So it's visible, just like you know public to mean that, right? Visible to the outside world, to the user. If you want that, we're not going to really care about that today. But that means, if you wanted to, that means other people could import it. Instead of include in Java and Python, by the way, it's called import instead. Could import it and use it. Right? So public class hello world. And then here's how you make a main function in quotes, of course. You make a static method, and it's called main. So you say public static void main. It doesn't return 0 or anything. It's void. Main is void for Java. And then the type, you can't give it like this. You can't just say parenthesis, parenthesis. You always have to give those command line arguments. They're explicit always in Java, even if you don't use them. And so it's, you don't give int argc and char star, whatever, argv. You just give an array of strings instead. You're getting an array of strings, and it's capital S for string in Java land. So string bracket bracket args. The bracket bracket is in the wrong spot. That's the new thing. In C++, it would have been like that. But in Java, it's next to the type, which actually makes more sense to me. It's an array of strings. It's all in one place. So that's your args. And so this is how you declare a main function. Right? So the main, in quotes, function, it's a static method, which functions like a function. The main function lives inside the public class associated with this file. So if it's hello-world.java, you're putting the main function, if you have one, in the hello world class. Right? Interesting misspelling. Public class associated. I get it. What I was trying to associated with the file. Excuse me. You must use this exact definition. So there's a lot of comments to this file today. You must use the definition below. You can't just like get rid of the args or anything. Args are your command line arguments though. Even if you're not using those command line arguments. It's got to be like that. Otherwise, it won't compile properly. It won't understand it. That's the main thing. That's where you want the program to start. Even if you're not using the command line args. Alright, so in Java, your arguments is an array of strings, capital S for strings in Java. And instead of saying public colon and stuff, in Java, you got to put public next to everything. Private next to whatever you want private. You got to say it each time, sadly. But I guess that's nice. At a glance, you can tell if something's public or private. Let's see. Main is a public method inside the hello world class. There's no concept of declaration and implementation as well. It's like you're just going to implement the thing. Just give it and give the implementation. There's no semicolon on main or anything, or any other function / method. Main is a public method inside the hello world class. It's also static. And static means that it belongs to the class itself rather than to any object of that class, which you'll probably have to read about that in your book to fully understand it. Which means that it belongs to the class itself rather than to any object of the class. Alright? And then you don't have to declare anything in Java, you just give the implementation and you're done. There's no such thing as declarations. You don't have to declare any functions / methods in Java. It doesn't exist. That doesn't make sense to it. It just finds them in any order. So like if you declare 2 methods and you use in the one above, you use the one below, it will find it. It doesn't care about order. It understands, which is kind of nice. It finds them no matter what order you put them in. Okay, so that's the main function. It's void, so all I want to do is print hello world, so it's only going to be 1 line. It's a very heavily commented file that's, 4 real lines. So to print something, you say system, this is disgusting, system.out.println ln to print a new line in addition. There's also just print. But print ln also adds a new line. And so you say hello world, exclamation point. You don't need the new line because the ln will do the new line, and then semicolon. That is hello world. All right? Any questions about that? Yeah. C# was modeled more after Java than C++, I would say. It's very, very much like C# if you know that. So, in a very real sense too, those are both, they both have virtual machines. So, one of the nice things about Java is they have great documentation. But one of the bad things about Java is there's so much in the standard library. That's either a good thing or a bad thing. Like here is everything in the standard library. Much, much more than C++ could ever hope to have, if only. So that's quite nice. And then we can find the print line. It was in the system package. It's in java.lang. That's imported by default. Inside of that, there is a system. There's a system class. And inside the system class, there is an out object. It's a static object that stands for your cout, essentially, your output stream. Its type is print stream. What can you do to a print stream? You can call print on it. You can print all these different kinds of things, or you can be println, all these different kinds of things, and we gave it a string to println. There we go. So that was a method on that. And so just like all this documentation is automatically generated. It's really, really cool. There's nowhere near enough time to tell you how cool it is, but that is Hello World in a nutshell. And so let's compile and run it. So in Java, you say javac, that's the name of the compiler. Let me know if I forgot to install this on the class server, by the way. I'll make sure it's there if it's not there already. Javac, you give it, and you say this. So here's your Java file, helloworld.java. You say javac, and you say javac helloworld.java. Hit enter. That's all you got to do. And that compiles it. And that makes a file called helloworld.class. That's the compiled form of our helloworld.java. And that's what we run, all right? You say Java. You don't say /. Java is a bit weird, and I'll explain that further later. But to run this program, you can't say / helloworld.class or anything. You say Java hello world without the extension. It'll go looking for the class file. Just say hello world by itself, hit enter, and it will run that program in Java land. Right? So there's our hello world. So that's how you compile, and that is how you run. So yeah, it'll just find the .class file. That's all. So that is the hello world example. Are we good to do some slightly fancier things? Show you some more things in common with C++. Alright, so yeah, pretty much everything in Java is a class. There are no pointers. Only things that Java calls references, which is going to be unfortunate given your C++ knowledge. And then arrays look a little weird. So let me just show you all that in one last line, one last file. I'll show you a bunch of types. Ints, doubles, booleans, strings with a capital S, arrays. And so I'll show you all this stuff. Dun, dun, dun. And then we'll talk about your final, and that'll be the day. But this is kind of exciting. We're learning a new language. morejava.java. Alright, so this file is called morejava, so the public class inside of it better be called morejava, exactly like that. Alright, if I want a main function, it's got to be public static void main string bracket args. There. And most things are very similar, like ints, int x equals 42, that's the same in Java. Double y equals 3.14, same as in C++. You don't do bool b equals true. You say, you got to spell it out in Java. It's boolean b. That's the difference. And then strings are capitalized, so string s equals hi mom. There's no separate library, it's already there. Arrays, this is interesting. Arrays must be made on the heap. Most things in Java must be made on the heap. So the bracket also goes after the type, just like here, rather than after the name. Goes after the type. And so this is what it looks like. Int bracket r equals, I don't know. I have to say new int bracket to make it, and then I can immediately fill it like this, 1, 2, 3. So that's the syntax, but it's made on the heap, new. I'm saying new. And all arrays in Java, which is nice, know their size. So I can ask for r.length, it knows that. Just baked in, which is pretty cool. So let me iterate through this and print out every element in the array. Let's do that. So for int I equals 0, I is less than r.length, I++, very similar, right? For loops look exactly the same pretty much. System.out.println r of I. It's an array. So that's pretty cool. And that's that. So I'm going to Java C, more java.java. Oh, thank you. I'm glad. And then it made more java.class, which I can then run. And run that file by saying java, more java, without the extension. And that prints my 1, 2, 3. That's pretty cool. Any questions about this code? Very similar. Slight differences. You might be worried about this new. It's not. Yeah, question first, though. No, this is a different thing. It's print by itself does not add a new line, but println does add a new line after whatever you give. Yeah. It's just a function call, not a weird looking cout statement. Yeah, any other questions? So yeah, you might be worried about this new, like, am I leaking memory? If I say new, I should be saying delete somewhere, right? This is interesting, because I get to tell you that there is no such thing as delete in Java. Only new. Weirdly enough. So no delete is necessary. Java figures out when you're done with something. Java takes care of deletion for you. It can tell when you are done with this thing, when you don't have access to it anymore, and it will get rid of it for you. It notices when we are finished with heap memory, and it gets rid of it for us. The verb is it garbage collects it. That's a fun metaphor. And it garbage collects it. So Java does memory management for us. And so there is a little bit of overhead. In general, the same program written in C++ is a little bit faster than the same program written in Java because of this. But they're competitors, that's for sure. So that's that. That's pretty nice. And then to run things in Java, it's a little weird. You say Java to run it. You don't say // It's not machine code. It's bytecode. So let me show that for you. It's like, first of all, on the heap, like Java is able to tell, like, okay, here are the things that you've made on the heap so far. I just noticed you don't have access to this anymore, so I'm just going to get rid of it for you. That's what it does. It's pretty cool. That's garbage collection. But before that, after that, let's talk about how Java runs its code. Java does not compile to machine code. It compiles to Java bytecode is the word. And it runs on the Java virtual machine. So you must install Java on your computer in order to run a Java program that's been compiled, right? Compiled Java programs. They're able, though, then to run on any computer with the Java virtual machine installed. They're all the same. It's not like, it's very different to C++. When you compile something for C++, you can only really run it on the same architecture. Like, if you compile it on the class server, you can only copy it and run it on Linux x86 architecture computers, rather than, like, you can't go and, like, send it to an ARM-based Mac or something. It won't work. Or you try to run it on Windows. It's a different operating system. But Java, you compile one place, it's always going to be the same .class file, which is kind of cool. You got to give it to the virtual machine, though, to be run for you, though. That's how that works. That's the give and take, all right? So that's kind of cool. So yeah, all arrays are on the heap. You have to say new to make one. Java is garbage collected. You say new. There is no delete in Java. And so here's kind of what's going on under the hood when you're running a Java program. You make your more Java file, I guess. .java. And then, like, you put your public class. ... You say Java C to generate the .class file, more Java .class, and this is not quite machine code. It's ones and zeros. It's a binary encoded thing. It's easily read by the virtual machine, but it's called bytecode, and this is the worst time for Zoom to get in my way. It's called bytecode. Java bytecode. And so you have to shove this into the Java virtual machine to actually run it. You can't just like give it to your CPU. The Java virtual machine translates it on the fly to CPU instructions that can be run quickly. Java virtual machine. JVM for short. And so it's just a black box that takes in your compiled bytecode and it runs it for you. It runs whatever the main function in that file was. It runs the code for you. So there's like a translation process between this and the JVM, like translates it into stuff that your CPU understands on the fly. It is called just-in-time compilation. It's a very complicated thing that you have to wait until grad school to learn about. So that, I think, is everything that I wanted to say for today. Are there any questions about any of this? We'll continue with Java next time, and then I want to talk about Python as well. So if we're happy. And I promise not to test or any of that. Containers, maybe. That's still C++. Java, no. All right. So I need to give you a lab. Let's do that. This will be due the 25th. So this is just like a week, but we have holidays, so 25th is the Saturday. Okay, just keep that in mind because Thursday and Friday are holidays. But this one is your square root lab. That's the one I promised, right? So you're doing that binary search kind of process to calculate square roots of numbers. So this is really, really fun. So here's what the code looks like. You're going to get it. You got all these files, and you're pretty much going to be working in square root.cpp. But what you're going to be doing is implementing a square root calculation program. These are the only two functions you need. Approx equal to see if you're close enough to the answer. So you'll make this, you'll take two doubles and give back whether they're very close to each other. True if they are, false if they aren't. And then square root, you'll use this function inside of your square root function. It takes a double, gives you back the square root of that number. So that's what you're going to be implementing. And you can make it work, I promise. So for approx equal, I want you to return true if these numbers are within this much of each other. So subtract them, absolute value, see if it's that. Okay? Less than or equal to that. So that's approx equal. And then square root is exactly what we were talking about. You're going to use a binary search style process, set up a low and a high, and like work your way towards the actual square root by guessing, checking the middle, and you're going to give that back. The only new thing, the only different thing is I want you to throw a runtime error. Put any string inside if you're given a negative number to take the square root of, because that one doesn't exist. So yeah, otherwise you're going to actually do the calculation. Runtime error though if it doesn't exist. So here's what you're going to do. In the square root function, you're going to set up a low and a high, and you're going to make guesses repeatedly until your guess becomes close enough, approx equal to the square root. That's going to be like the condition of your while loop. All right, as long as it's not approx equal, close enough. Okay, so you're always going to keep getting closer to the answer because this is a monotonically increasing graph that we're trying to approximate and solve for. So square root of x is not defined for negative numbers, so throw a runtime error if the user gives you a negative number. But if, for example, they gave you 5, here's the setup. You're going to set up like a low and a high variable, and you're going to make a guess. You're going to be like, all right, they square root of 5. I don't know what it is. I'm going to search for it, but I know initially the answer is somewhere between 0 and 5, right? That's always the case for most numbers. So at the very beginning of your function, your search space always has a lower limit of 0. That's the lowest possible square root. And then an upper limit needs to be the maximum of one integer number. So if it's 5, the upper limit is 5. If it's 42, the upper limit is 42. But if the number that you're trying to take the square root of is 0.5, you need 1 as the upper limit. Does that make sense? Because the square root of 0.5 is bigger than 0.5. That's important. You could also just say x plus 1 could be your upper limit, as long as you have it within your range. So you'll run into issues with small numbers if you don't do that, but usually it's the number itself. You're going to repeatedly guess in the middle, right? 2.5 is going to be your first guess. That's going to be a little too large, and you're going to update your guess, okay? You'll repeatedly calculate the midpoint of your search space, check and see if it's good enough, a prox equal, like you're going to square it, right? Square it and see if it was the original number. That's how you check if the square root was correct. And then you're just going to keep on updating. So here is, I've been very nice to you. Here is an example. If you were asked to calculate the square root of 9, here's exactly what your code should do. All right, I've printed out each iteration, what it should do. This is how your program should think. Model it after this. All right, so if you're given 9 to take the square root of, here's what you do. The lower limit is initially 0. That's the lowest possible answer. And the upper limit should be 9. Your low and high. 0 and 9. I don't know what the square root is, but it's between 0 and 9. That's what you're saying. All right. Then you calculate the midpoint of that search space. In between 0 and 9 is 4.5. Yeah. And then you square it to see if you were right, if you were close enough. Squaring 4.5 gives you 20.25. That was way too high, right? Your guess for the square root was too high, so it's definitely smaller than the mid, so change your upper limit to be the old mid. So now we're in iteration number 2. With the lower limit 0, the upper limit changed to be the old mid, 4.5. So that process makes sense. So you're going to do that a bunch of times, all right? Now you know, all right, you have some more ideas. You're like, all right, I have half the space to look through. I'm going to get a better answer this time. So you're going to calculate the mid of your current search space, which is apparently 2.25. That's between 0 and 4.5. You're going to square that because you're solving for the square root, right? You don't know what that is, but if you square the square root, it should give you 9. But this one is a little too small. 2.25 squared is 5 something. So that's too low, and we should guess higher, which means that mid is going to be bigger than mid, so change the lower limit now. You see that? So now iteration number 3, this is your range. It's between 2.25 and 4.5. You're cutting off half the space each time. You're getting closer and closer to the right answer. So the midpoint of this range is 3.375. You square that, you're very close. You're getting much closer now. It's 11. So that's too high, which means that mid should have been the upper limit. That's a better upper limit. 4.5 is way too big. Okay? So again, iteration number 4 now. Keep the same lower limit. The new upper limit becomes the old mid. Right? You square that. It's mid is this. You square it over here. That was a little too low, so guess higher. Change the lower limit now. That means mid was a better guess for the lower limit. So now you have this range. And you're slowly but surely getting closer and closer to the right answer. You see that? So what's the midpoint of that? It's that. You square it. It overshoots 9, so it's too high. That means mid is a better upper limit. 3.375 is too big. So keep the lower limit, new upper limit. Calculate the midpoint. Square it. Now it's too low. So that means mid was a better guess for the lower limit. So it's going to be bigger than that. So change this to be that. So now your lower limit's that. Upper limit's that. Mid is this. Mid squared it's getting so close, but it's not approximately equal yet because we went to a bunch of decimal places, right? So now it's too high. Guess lower. Change it, change it, change it. Apparently, you need 25 iterations. So iteration 24, here's your lower limit, upper limit. You square it. It's still a little too low. You say guess higher. You change your lower limit one last time. Your last iteration. Lower limit's this, upper limit's this. Your midpoint is 3.0 with a bunch of zeros. Oh, man. And then you square that. You find that it is approximately equal to 9, so you return mid as the square root. Does that make enough sense? So just try to get that working. You don't have to print anything out. It's like you're returning the square root, but this is how your program should think, okay? So definitely use that as a guide. So yeah, the idea is eventually the middle of your search space, square it, will become approximately equal to that original value you're trying to take the square root of, which means it was the square root. Yeah.
So are we going to return the 3.00001?
Yes. That's what you will return, even though it's not exactly the square root. It's an approximation of it to some amount of decimal places.
I guess my question is, you don't want us to fix the number up and make it look nice.
No, because that would just mean you running more iterations. No, as long as the second it becomes approximately equal, that's a good one. That's close enough for our purposes. Yeah. And so yeah, get that working. It's not too horrible once you get the idea and how things change. It's going to be a loop though, and do watch out for negative numbers. Just throw a runtime error immediately if you ever see one of those because you can't do the square root of a negative number. Yeah, so once you got that, do some tests too. So I've given you some tests already. And for no good reason, I made a class this time to do tests. So it's a class of tests. So I've made some methods. This is square root of 2, making sure that it's very close to the right answer. Square root of 0.5 is very close to the right answer. Square root of a negative number actually throws an exception. So get those to pass. And then I would like you to write 4 more tests, just like pick some random numbers, make sure that the square root is those. Something like that. Okay? So get 4 more tests passing after you've got mine. And that is pretty much your lab. Are there any questions about anything? So I've given you a make file this time. You're welcome. You'll say make. You can just say make, honestly. Or you can say make square root test. The first rule is the right rule. So you can just say make, or make square root test will make the final executable and compile everything separately. Cool. So you can say make square root test, or just make to compile everything, and then you run it like this. Right. So you make 4 tests after mine are passing, and then because you wrote tests, you're also going to turn in the testing file. Okay, so those are the 2 files that you turn in. And that is your lab. So I've tried to explain it as thoroughly as possible. Just follow my lead and get it done after Thanksgiving. Are we good with that one? All right. So you also have a test coming up. So we are in week 15. Week 15 of class. There are 17 weeks of classes. So there's lectures up through week 17. Week 18 is finals week. Okay? So do not pay attention to this date right here. It's probably wrong. But I'm going to release the final info page and the extra credit assignment page, because with every test comes a new extra credit assignment, as we know. And let's look at both of those. So week 18 is when our final is. And so our final, apparently, I read it off of the table. Hopefully you can confirm that this is correct. But this is what I put in the syllabus too. This is what it should be, right? Our final is going to be in this room from 2 p.m. to 3:50 p.m. That's how long we get. An hour and 50 minutes to take a final on Thursday, December 7th. All right, it's the Thursday of finals week. So you don't show up on the Tuesday. It's finals week. There is no class, but Thursday is when we have our test. So there it is, the 7th. Thursday the 7th at 2. Okay, that's when it's going to be. And then the topics are all these. So it's like, expect to see everything. You know that you're going to have loops, right? Those exist forever. I can't just say it's only the stuff after the second midterm. So assume it's comprehensive. I'll try to give more weight to questions based on things that we've covered more recently after the second midterm. But here are the things. Here's a list of things, at least, that I want you to be very, very ready for. One thing I won't do about pointers, though, is I'm not going to test you on pointer stuff that I didn't talk about in lecture. Like, for example, linked lists and destructors and stuff like that. You read about that. That's preparing you for 41, but I'm not testing you on it in this class. Okay? So that's that. And then everything that came after bitwise operations, I won't hit as hard, but still expect some questions on that stuff. I promise to make them easy if I ask you anything about those. But those are the topics, and same setup as before, open book, open notes, can't talk to a human other than me, and then here's a sample final. Okay? Any questions about the final and how it's going to work? So that's when it'll be. And then here is your extra credit opportunity. So the final happens on the 7th, so I'll give you until midnight on the 6th to get in this extra credit opportunity. It's worth up to 5% extra credit if you would like. So here's what you can do if you would like it. Again, make a review video. I don't think I have to explain this too much anymore, right? So make a video that has a bunch of examples of you being creative and making up them and like just demonstrating stuff that might appear on the final, going over things, making fun slides, fun example code, stuff like that. Okay. So if you want 1.25, a little bit of extra credit, 1.25%, make a 10-minute video. You want double that, make a 20-minute video. You want double that, make a 40-minute video. Okay? So have a lot of examples. Make it fun. Make sure that you're not just like reading off my slides, reading off the textbook, going over code that you wrote for a lab or something already for credit. you must make something new. Okay, make sure that you're doing that. Otherwise, I won't give you credit because that's not extra enough. So when in doubt, ask me about it, and I'll make sure to tell you if I think that's a good idea or not. But I trust you to make something new, and that is your main requirement, and go over it. All right. So yeah, that's your extra credit assignment due midnight before the test, and I think that's all I have to say. Questions about that? All right, that was a lot that we had to talk about, but I'm finally done with it. So that's everything that I wanted to talk about today. The rest of the time is yours to work.